third and last speaker in this session, before we have the discussion panel, is Pierre Fouque, who will talk about fairness of systemic risk measures.
Thank you very much. Thanks for the organizer to invite me again here in Brazil. That's not my first time, maybe fifth time. I don't remember exactly, but so this is always a great pleasure, and it's a great pleasure in honor of Bruno. Bruno has been very supportive of what we have done the last 13 years at UCSB, so thank you for that. I will say more maybe later. Speaking about Santa Barbara, I have a good incentive to be short. This evening, this is the last talk, you're all tired, so I have 45 slides, but I will compress that in 20 and forget the second half. But I have another incentive, and 6 months ago, I was sitting in my backyard in Santa Barbara, and I had this magnificent show in the sky, this rocket shooting to Mars. And the probe is not landing on Mars in 40 minutes. So I would like to see that on the live feed, so I will go quick and see the landing of the InSight probe. So I've seen it 6 months ago, and I want to see it landing. So that's my introduction, already 5 minutes gone. So I want to talk about fairness of systemic risk measures. This is a work with my colleague Marco Fritelli from Milano and Francesca Biagini and Thilo Meyer-Brandis from Munich. We started this work some 4 years ago, try to address the possible definition of systemic risk measure. And by the way, this has nothing to do with volatility on purpose. We have a lot of volatility here, so this is not on volatility. And so we introduced a class of systemic risk measures that I will recall the definition in a very simple way. And one question arose after this introduction was the fairness of allocation of risk. You have several institutions, several banks. You give risk allocation, and you want to allocate risk and maybe rank your institution in terms of systemic riskiness, and that's kind of an important question, and we try to address it from the foundation and not really looking at data. There is no data in this talk. It's basically a foundation of extension of risk measure to the case of an institution systemic risk measure. Okay, so first I will give you a very brief introduction to risk measures, so that will be one slide. I guess everybody knows what is a risk measure, but I will recall that. But then I want to introduce this systemic risk measure that we identified with my colleagues in this paper in Mathematical Finance this year, actually published this year. So, and one of the discussion here is how do you aggregate risk? Do you aggregate risk first and then inject cash, or do you inject cash in all the institution, aggregate the risk, and try to optimize? So this is what I want to recall in a couple of slides. That's what we did. But the main question here is the present paper. So this is submitted on the fairness of allocation. How do we qualify our allocation of risk? And this raised a lot of mathematical questions. And hopefully, I think we have the right answer. And I will show you the answer without the mathematics because it's getting involved and the paper is quite long, but it's on my webpage, you can find it. And so that's, and actually there is another paper following that, but I will talk about that at the end. Okay, so very quickly, so this is the classical concept of risk measures from Asner, Delba, Neber, and Heath in '94, and then following work, where you have a random variable. So this is a set of random variables. And to a random variable, you want to associate a number. And this number is defined as this. So you have a set of acceptance sets, A, of random variables. So you have your position. X is your position. It's one-dimensional random variable. You add cash to it. And you want this position to be acceptable. So everything, of course, depends on how you define acceptable here. You have to define what class of acceptability you want to work with. And then you take the minimum amount of cash that you need to inject to be acceptable. So that's a very classical definition. And then there are some additional properties which make this risk measure coherent, for instance. If you think everybody knows about VAR, value at risk, which is not a coherent one, but you have plenty of examples, and I will show you particular example that we have in mind here. Okay, so this is just to recap the system risk measure, add cash, make the position acceptable, compute the minimal amount of cash that you require for this. Right? Now, the second ingredient that we will be using in a minute is this remark by Fritelli and Scandolo in 2006, is what you may want to use other things than cash. You may want to use other instruments that you can add to your position. And let's say you have a set of instruments that you can use. This can be derivatives, this can be a lot of things. And you can use this set of instruments here that you add to your position, and you want to make the position acceptable. But now you have to measure the price of this instrument through the pi of y is a price, and you take the infimum of that. This is your new risk measure, your new capital requirement by using a bigger class of instrument than just cash. Right? So that was what Fritelli and Scandolo brought in 2006, and we will use this remark here. Okay, so now systemic risk measure. So the situation is that you have n institutions, so you have a vector of position, right? So we go from one-dimensional to n-dimensional. You have a vector of position, and we want to define, again, an application from these random vectors into real numbers so that we describe the systemic risk measure of the system, right? So again, here, I mean, this is very simple. You have to, there is no time. There is present time and the future time. That's it. X is your position at future times. There is no dynamics. Everything is static. So one-period model. Okay, so initially in the literature, you will find a systemic risk measure defined like this. So this is an aggregation function. You take an aggregation function of the risk. So lambda goes from Rn to R. You get a new random variable, and now you can use your favorite risk measure already defined to compute your systemic risk measure. So this is where you aggregate first and measure second, right? So that is kind of classical, which has been done since 2010. I will give a couple of references later on. But we want to discuss another way to do that. Let me first show you some example of aggregation function. For instance, you can do the sum. You just do the sum of all the position. This is a pure subsidization of banks between banks, so maybe this is not really acceptable. You have the sum of the shortfalls with a given level. You have something which is a little bit more smoother with an exponential, and this is the one which is very smooth. And this is a sum of utility function, and the exponential utility, that's the one I will be using in the example at the end. But in all we do, we assume that this lambda is a sum of utilities. That's the choice that we are making here. So these are examples, but basically we will be in this setting, and this will be our main example. So now, of course, so if we do it in the usual way that just presented before, you aggregate the risk, you add cash, and you want to be admissible, compute the infimum of the amount of cash that you need, and this is your systemic risk measure. So this has been done in several papers here. I'm not reading all the names, but there are axiomatic approach to this approach of aggregating first and then adding cash. So we want to depart from that, and what we proposed in the previous paper, in the one which is to be published in Mathematical Finance, is the following. So instead of aggregating first, inject cash. So now you inject M1 in bank X1, M2 in X2, Xn in Mn in Xn, and then you aggregate the position, and you want to make it acceptable, and you compute the total amount of cash, and you want the minimum of that. So it's an optimization problem in n dimension, right? Okay, so I guess this is fairly simple to understand what we do. Just allocate cash and then aggregate and then compute the minimum. Right? So this was very nice, and this has been, I mean, we introduced that, but it was also discussed in a little bit in parallel with some differences by Feinstein, Rudolph, and Weber in 2017. But they have a set valued risk measures. We have a risk measure, so that's a little bit different. And also, this was also discussed in this paper here. Stefan is somewhere here. Here. Good. So, now the next step, and maybe a remark. This is interesting because when you do that, then if you have an optimal here, an M star, let's say, suppose it's unique for a minute. If you have an M star, this M star is a good tool to rank all the institutions, right? Now you can measure the risk of each institution by looking at the M star associated to this optimization problem, right? So that's a ranking system of the institution. Well, now we want to go a little bit further and use this remark by Scandolo and Fredeli and Scandolo, where you can use other instruments instead of just cash. So that is what we propose here. So instead of doing that, we introduce a set of random variables that you can use as instruments. And this set, so this is a notation here. First, this notation means that this random variable is, so this is a sum. The sum of the y's is in R. So this is an n-dimensional random variable, random vector, but we want that the sum is a real number, is deterministic. So this is a class of instruments so that the sum is deterministic. The reason for doing that, I will explain in a minute, the reason for doing that is that the amount of cash that you want to inject in the system in the future may be scenario dependent, but at time 0, you want to know exactly how much cash you need. So this is this requirement. This means that at time 0, I know the amount of cash that I need, and then I will allocate it in a scenario-dependent way. Right? And I will give you an example in a minute. So our risk measure now is, again, the same thing. Allocate your instrument to each institution, aggregate the risk, make it acceptable, compute the minimum of these numbers. These are numbers, they are deterministic. Compute the minimum of this number, and this is your systemic risk measure. Yes? What the, sorry? Deterministic, you mean? Why it is deterministic? Well, maybe there are other choices, but this choice is from, and we will see it is from the point of view of the regulator of the society. It means that at time 0, you know exactly how much cash you need. It's not a random variable, right? You don't want a random variable at time 0. You want something known. And then the allocation will be scenario dependent. So maybe there are other ways to do it, but this is the way we choose. Well, okay, so, yeah, okay. Okay, so this is the scenario. I prefer to say scenario dependent than random allocation. Random allocation sounds a little bit weird that you throw money at random. That's not what it means, of course. The two extreme cases, if C equals Rn, you are in the previous situation. Now each of the allocation is deterministic. If C equals CR, it means that you have full subsidization between banks, and that may not be completely desirable, right? Okay, so let me give you an example. This is a very interesting example in order to do computation and understand. Suppose you have groups in your institution. Let's say you have insurance, banking, mutual funds, trading at different time frequency, trading volumes with different goals. So these are the groups. And what you want as the instrument, you want the instrument to be in each group to be a deterministic function. So you want a deterministic amount of cash for a group, right? And that group is, they agree to share the risk. The group agree to share the risk. So this is from an idea from insurance. In insurance, you have this situation. And then, of course, the sum of the y's is simply the sum of the d's here, the sum of this amount of money. So this is a very, very interesting example that we will discuss later on. Of course, if you have n groups, then you have deterministic allocation. If you have one group, it's a full subdivision. Okay, so the first thing is that, of course, from one advantage is first that you reduce the systemic risk. Because you have more instruments, you will reduce the systemic risk in some sense, the measure of the systemic risk. The second the second advantage here is that you take into account the correlation between the positions. So let's look at this example. Suppose I take, as we said, the sum of utilities. We are always in the case of sum of utilities. And you take as admissible set this condition that the expectation is greater than some level. Right? That's a perfectly nice admissibility set. And so what you want to do is you want to add your position here, and compute the sum of the utility of this sum. So of course, if the YNs are deterministic, these look only at the marginal of x, right? It only involves the marginal of x. Now, by taking YN being scenario dependent or random, then you bring back the correlation between the positions. So let me illustrate that here. For instance, if you get so I think this is fairly clear. I mean, the fact that you only look at marginal if you use only deterministic allocation, and then this will allow to cross-subsidize. So of course, you are using the correlation. I will show in a minute or 2 minutes the example of exponential utility where all this is computed explicitly, and you will see how this is working. Right? So fairness. So the question is fairness. Yes. Yes, 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 absolutely, but less tractable, less tractable. Yes, that's what you want. Okay, so fairness. The problem is since we want to use random allocation, we need to price those random allocation and use that as your ranking, for instance, of riskiness. How do you allocate the risk? So here we allocate money. Let's say we allocate cash. This is a cash amount depending on the scenario, but yeah, that doesn't give you any handling of the ranking of this allocation because they are random, right? So what you would like is to measure the price of this YN according to some measure so that the ranking is fair for both the point of view of the institution, individual institution, and fair from the point of view of the society or the regulator, let's say regulator. Okay, so this is a question of fairness. It's not a well-defined concept. Of course, mathematically, you have to say a little bit more, but this is the idea. How do you price those YN? So you have the infimum here. How do you price those YN so that the risk allocation is fair? Right? So risk allocation, let me go fast a little bit. The risk allocation, so you have to put some integrability condition, which I will skip.
Jean-Pierre,
yes.
The one question is fairness. The other one is not giving a wrong incentive to institutions to take more risk than they should. Is that two parallel questions, or?
Yes. So the regulator basically is imposing the kind of systemic risk measures that he will be using. That is the imposition of the regulator, but it has to be fair in the sense that this will be measuring the individual systemic riskiness. So, and the bank could say, well, but this is not fair. I have to share the risk with other banks. It's not fair to me. So how do you price those YN so that everybody is happy? So when I say that, of course, you should think about equilibrium somewhere, and this is what I'm getting at. So let me skip the gory details about all this space, but you need some integrability, and that's a little bit. So let me give you the definition that we take for risk allocation. So the first thing is that I recall the definition of the systemic risk measure, and I say this is a risk allocation when I measure the price of my X, right? So this is a way to measure the price of random variable. So I need to find those rho n. Which are the rho n which are fair from the point of view of an institution and from the point of view of the. So now let me give you the answer, and I won't go into the details, but here is the answer. So first, question and answer. So the question is, what is the set of valuation of this optimal risk allocation so that this is fair from the whole system? What is the set of risk. So this is risk allocation. This is random allocation, and this is risk allocation, the measure of what you inject. How is it fair for the whole system? And then, of course, why this is fair for each individual bank, right? So these are the three questions we would like to answer, and basically the question is which row n should I choose, right? So here's the answer, preview of the answer. So these are the optimal random allocation from our minimization problem, right? So the systemic risk measure, of course, is a sum of this optimal allocation. That's a deterministic number. And then I introduce the dual problem. So I have a minimization of the optimal. I introduce a dual problem, which the solution of the dual problem will be a vector of measure. And this rho n defined as the expectation of the yn with respect to the optimal dual measure is the fair risk allocation that we propose. And the paper is about answering those questions. So first, what is a dual representation of rho x? Because now we are in n dimension. What does it mean? How do you compute it? Second question, why do we have existence of the optimal qx? Do we have existence? Do we have existence of the yx? Yes, we have existence. And why it is fair? So that is the rest of the paper. And it's a little bit complicated to go through the details. Let me just give you one theorem. So this is existence. This is how you define the dual. You maximize the sum of the expected, negative expected in this case. And you have a penalty function. The penalty function is given by this. And it has to take into account the set of y's, which is in the domain of the penalty function. So the set of instrument that you use appears in the domain of the penalty function. So in 1D, this is well known. This is the dual problem as well known. That's a little bit less known. And this is what we discuss in the paper. And this is a way to compute. If you want to compute the penalty function is given like that. Of course, it introduces the convex conjugate of the utility function, and you have to compute all these convex conjugate and derivative, solve this equation, put that back here, you have the penalty function. So there is a lot of mathematics behind it. But what I want to show you is the example of exponential. So I will skip all these. Tac, tac, tac. So these are all the details of this. I will skip that. Maybe this last thing. What we show in the end, is that the individual institution, if the individual institution is solving its own optimization problem, that's what the individual institution was to solve, given the price of what you add, maximize your utility. So it's a maximization utility problem. And it turns out that yx, qx, and actually the price form a Pareto equilibrium. And that's work in progress and will be submitted soon, I guess. This is for those who know a little bit about insurance. The idea was in Bullman in the 80s for risk sharing. So this is really the idea of capital allocation sharing, if you want, instead of risk sharing in insurance. So it has the same flavor. And so the next paper will be about exactly describing that this form a Pareto equilibrium for this problem, which makes sense. And now let me show you an example. So we do the grouping. So when you do the grouping, the Q is the same on each group. So you have one Q per group. And when you look at the exponential case, so these are the exponential utility for each group, and with one parameter for each group. You can compute, of course, the Legendre transform. You can compute everything, compute explicitly the penalty function, which involves the relative entropy of the function. So these are very, very simple to do. And what is more important is that you can really identify the new measure. The new measure that you need to define fairness is given by this ratio here, where x bar is the average, is a sum on the M group. So this is fairly explicit. So you just compute explicitly what you have, and you have the density. You have the definition of QXM. Okay, so this is, and there are a lot of other things. sensitivity analysis and a lot of things in this paper that I will just how the covariance is going back. And I want just to be on time for you to relax before the dinner and for maybe watching this landing on Mars eventually if it's successful. And the poster, watching the poster. And so the paper is on my webpage. And finally, thank you and joyeux anniversaire, Bruno.
Well, thank you, Jean-Pierre, and thanks also to the other two speakers. So now we have time for questions for any of the three speakers.
So I have a question for Jean-Pierre. So I So I understand in abstract the definition of the risk measure, the amount of cash that you would add to the portfolio to make it acceptable. But I have trouble understanding how you operationalize that because you said the regulators would then put this cash into the banks. But in practice, there are different ways of doing that. So the banks can borrow from the central bank. The banks can sell something to the central bank and raise the cash, or they can raise capital. And each of those things will change their portfolios. So now, once you operationalize this amount of cash, now it's a different random allocation that you have.
No, so, make it short. I mean, think about capital requirement. You can think about it as capital requirement. This is a capital that requires a bank to all. This is working. Okay. And so that's one way to see it. The other way to see it is that actually there is no exchange of money at all. So this is a measure of systemic risk. That's a mathematical computation that you want to do to measure the risk of the future position. And you may not have any exchange of money. Right.
So that interpretation I understand and agree, but the first interpretation, like the capital that you have to raise, but how do you raise capital?
The bank, each institution is
So how do they do that?
Well,
they have to sell shares, and selling shares will change their portfolio.
The feedback effect.
Exactly.
I agree. Okay. When you come back to Santa Barbara, we will work on that.
Also a question for the systemic risk. So usually these allocations are kind of derivatives or like subgradients or stuff like this. I saw on this slide you skipped also some derivatives.
No,
so it's and so if it's an insurance, if you have let's say a non-coherent risk measure, you have all this Shapley allocation, which is also kind of a mixture of derivatives.
Yeah, so what I have in mind more than derivative, I mean, initially when I was addressing this problem, is more like you want the allocation to be depending on the state of the economy or the state of the banks at time one, at future time. So for instance, you look at the sum, total capitalization. If the total capitalization is above a certain level or below a certain level, then you don't allocate in the same way. That's what I have in mind. So this is not really derivative. Derivative is another way to do things, but here it's really scenario dependent. Depending on the total capitalization of the system, I will allocate differently. So this is not derivative. This is already random allocation. This is more what I have in mind. But then you can retranslate it on derivative return on the total capitalization, right, in some way. But you have to measure the price of that.
Hi, quick question for Raphael. Do you use just price data to fit your HMM?
Do I use price data to fit?
Your
That's exactly it. So basically, the way I did it that you start with, for instance, you have a market in which you want to invest. Let's assume 500 stocks in the S&P.
Yeah.
And then so you calculate all those covariances, regular basis. They are the very big covariance matrices. It's very difficult to I mean, as soon as you change slightly from one period to another, you get distributions that are very far apart.
Yeah.
So the thing that you first reduce with, you use, industrial sectors, and then you can also, even include something that are not specifically in your investment universe, but that define regimes, such as interest rate, FX, other markets, etc., emerging markets, for instance, and that can potentially impact the investment universe in which you are. Total, we went to something like 17 risk factors, which we monitored. So our covariance matrices, they were 17 by 17.
But you use also external data. In my experience, I always use HMM or other regime switching model. Very difficult to outperform a very simple exponential moving average.
Absolutely. I mean, that's
but
what I was saying.
If you use like, now it's over 50 exercise because 2007, you know what happened, but you have the TED spread, the quant quake. You have a lot of external variable margin.
So that's why I was telling you. I mean, however, we still use price and rates because you need things that are quoted every day because you want to look at daily correlations.
Yeah.
Mm.
Cool. Thank you.
Okay, so in the interest of the posters and the Mars landing, I suggest we keep the questions and the answers short now.
A question to Jean-Paul. So imagine a country with systemic risk measured for all the banks, and now the crisis, most of the banks do bad, but one bank is just fantastic. You can't just grab the money from the good bank and cover the deficits of the others. So
that's exactly where you, let's say, grouping, for instance. In the example of grouping, you will have group of institutions they have agreed to share the risk, right? Of course, if someone doesn't agree to share the risk, it will be alone in his group, and his allocation will be deterministic. So it's a sharing mechanism, right? Yes.
Yeah. I mean, and correct me if I'm wrong, Jean-Pierre, but the allocation of capital is a bit similar. It's not exactly the same thing, but it's a bit similar to the fact that when you do portfolio allocation and optimal allocation of portfolio, in fact, you will find that the allocation has to be, the risk contribution has to be proportional to the return contribution of every single component of your portfolio. So in here, the risk, that the capital that you have to assess to each bank is proportional to its contribution to the global risk. So in some sort, it's the risk of the institution multiplied by its correlation to the global risk. So if one bank is very aligned with the global risk, it will be required to have a bigger capital than another bank that is completely orthogonal to the global risk, that will have a less of a contribution to the systemic risk. So that's the general picture.
Yeah, in the case of portfolio, it really makes sense to do the sum. The aggregation is simply the sum. Yeah. In that case, it makes sense.
And you always have a solution, that's what you put, that there is always
for the Q. For the dual. Yes.
Because I had this discussion with Kavanaugh, and
yes.
that was not on the case.
No, because the dual was not in the picture before that paper. You have existence and uniqueness for the dual.
Okay, last question.
This was a question about the dual. Do you have some sort of Kusaka-like representation for those measures, or?
Not really. The only representation I have is the one that I showed you. There may be something else, but this is so far the only one that we have.
Okay, so I suggest that at this point we close the discussion and thank all the speakers of this session and also of today.